In this session, we will learn about artificial neural networks and their applications to generative art and computational creativity. But first, I think it might be useful to say a few words about machine learning and before that, about learning in general. Learning is a very general term denoting the way in which agents acquire knowledge by gathering information and building a coherent model of some external reality. This includes developing theories and models to explain observed phenomena. Learning can also refer to agents improving their motor or cognitive skills through repeated practice. In all those cases, learning results in changes in the agent's behavior that improve its competence or efficiency. Competence and efficiency are often considered the two complementarity dimensions of learning. A system's competence is considered to be improving if it becomes able to solve a greater variety of problems with fewer mistakes. Competence is both a question of generality and accuracy. Efficiency, on the other hand, has to do with whether the system learns to solve the problem from its area of competence faster or by using less resources. For both of these dimensions of learning, there have been attempts to develop algorithms to do exactly that with artificial agents. Artificial intelligence is a science and engineering concerned with developing systems that exhibit the characteristics we associate with intelligence in human or animal behavior. Machine learning is the domain of artificial intelligence concerned with building adaptive computer systems that can improve their competence and/or efficiency through learning from input data or from their own problem-solving experience. Machine learning theories and techniques draw inspiration from many disciplines: artificial intelligence, data mining, probability and statistics, mathematics in general, information theory, numerical optimization, computational complexity theory, and control theory. Machine learning also looks to neurobiology, cognitive sciences, including developmental and cognitive psychology, linguistics, and to some extent, philosophy. It is a really interdisciplinary enterprise. Machine learning has been defined by Herbert Simon as any process by which a system improves performance from experience. More formally, the idea is to improve on a task with respect to a performance metric based on experience. What type of task can we learn? Some categories of tasks that are typically learned are classification, problem solving, clustering, and generation. Classification is where you assign an object or an event to one of a given finite set of categories. For example, recognizing dogs versus cats, or recognizing the author of a composition. The equivalent to classification in continuous domains is called regression. Examples of regression tasks include predicting the value of the market, the value of a function, or judging how interesting a painting is on a continuous scale. Another class of learnable tasks is problem-solving, planning, and control tasks. These tasks involve performing an action or a sequence of actions in a given environment in order to achieve a goal. For example, finding a path in a city to go from A to B. Then there is clustering, which is the task of partitioning examples into disjoint subsets of clusters so that the examples within a cluster are similar to each other and the examples in different clusters are dissimilar. That is, for example, trying to cluster groups of customers to see if there's some types of customers that can be delineated, or clustering a set of music composition to see if several distinct styles are present in a corpus. Then there is the generation task, which is to produce likely data. That is, data that follows from the statistical model of the input examples. The generation can be complete or partial. For example, an agent might generate new recipes given what is in your fridge, or an agent might generate a joke, or generate an interpretation of a piece in the style of a known pianist. There are different types of learning for those different tasks. Classification and problem solving are often learned with supervised learning. Clustering and generation are most likely to involve unsupervised learning or hybrid approach. In supervised learning, we provide input data so that the system does its task. Since we know what the system is supposed to do, that's what supervised learning means, we can measure the distance, if there are any, between what the system does and what the system is supposed to do according to the training data. This is what we call the error. If the system is learning how to distinguish pictures of cats from pictures of dogs, then each time the system makes a mistake, the supervisor can tell it so. and eventually elaborate on the type and magnitude of the error made. The system uses that feedback to learn. That is the idea of supervised learning. In unsupervised learning, the learner is confronted with the input data. He does the task with no feedback about whether the task was well done or not. As you might have guessed, hybrid learning mixes the two. Here are some more examples of each group of tasks. In classification, the task is to assign objects or events to one of a given finite set of categories or classes. There is a really massive number of applications, and this list is just the tip of the iceberg. The same is true for problem solving, planning, and control, performing actions in an environment in order to achieve a goal. Here is a list of examples. All those examples are planning and control problem solving. Clustering is creating classes for data and classifying them, reducing the number of dimensions. Here is a list of examples. And finally, generation is the task of generating new unseen data that follows the model and distributions of the input data. For example, there is composing music in the style of Bob Marley, generating rhythmic patterns for a given bass line, or generating a rendering of a given picture in the style of another. Those are all generative tasks that have been addressed. We can typically represent a learning problem by defining the task that is supposed to be learned, the experience and data that the agent can use for the learning, and the performance or competence measure that indicates how successful the learning was. Here is how to apply the task, experience, performance view of machine learning systems to some of these examples. Let's assume that the task is playing checkers. The experience would be playing practice games against itself or against a human player, and the performance measure would be the percentage of games won against an arbitrary opponent. Here is another example. Let's assume the task is to recognize handwritten words. Here the experience comes from the database of human-labeled images of handwritten words, and the performance measure could be the percentage of words correctly classified. Let's look at the case of generative tasks. For example, the task could be to generate a composition in the style of the Beatles. The experience would be having access to the songs of the Beatles and maybe some other pop music. The percentage of human classifying a given generated song as a song of the Beatles or similar to a song of the Beatles could be the performance indication. In modern machine learning, there are mostly two ingredients. One is the way things are represented, the representation language that is used for the possible search space or hypothesis space as it is sometimes called. The other is the search technique that defines the way the search space is traversed. The design process involves choosing exactly what is to be learned, that is, the target function. Learning can be viewed as using direct or indirect experience to approximate a chosen target function. The second step is to choose how to represent the target function. The third step is to choose the training experience in the supervised case, or find the input data in the unsupervised case. The fourth step is to choose a learning algorithm to infer the target function from the experience. Function approximation can be viewed as a search through a space of hypotheses for one that best fits a set of training data. Different training methods assume different hypothesis space or representation languages and employ different search techniques. There are a wide variety of possible functional representations. Numerical functions, which can be learned as linear regression, neural networks, or support vector machines. Symbolic functions, such as decision trees, rules in propositional logic, or in first-order predicate logics, or grammars or final state automata. Instance-based functions, such as nearest neighbor or case-based functions. Probabilistic graphical models, such as the naive Bayes model, Bayesian networks, hidden Markov models, or probabilistic context-free grammars. Agent as a function, which can be learned through reinforcement learning, Markovian decision process, or learning to communicate, or even communicate to learn. The functional representation is what is being learned. Then those such spaces of possible functions or representations can be traversed and learned using a variety of learning algorithms. These include evolutionary computation that we already studied in this class, but also dynamic programming, divide and conquer, and gradient descent, which we will study in our session on neural networks. Machine learning is the power tool of AI, and with the digitalization of society and the tsunami of data we are living through, it is a game changer. Be it for rational problem solving or for the creative applications we study in this class, it automatically learns how to achieve complex tasks, resulting in processes that are more complex and accurate than those that programmers can produce by hand. This concludes our short introduction to machine learning.